students. Welcome to our first online session for the course Digital Logic Design uh, with the course code 22241. My name is Ali Roman and this is our first interaction, and this session is specifically designed for the students of Bachelor's in Software Engineering 3C section. So uh, let us first see the contents which we will be covering in today's session. So basically, we will be having the introduction to the course, and then we will be discussing some basic primary gates, logical gates that are used for the logical assessments and that are basically utilized while designing digital circuits for the digital logic design. And we will discuss AND gate for a AND operation. Afterwards, we will discuss the OR operation, then NOT operation or the inversion, then NAND and NOR. And if you got some time, then we will discuss exclusive OR and exclusive NOR gates. So before starting our session formally, this course basically was assigned to Dr. Sadek, and till now you have covered about the basic concepts regarding the digital systems. You've learned about the numbering systems, and you've discussed that how to convert from one base or regex to another, or to migrate a number from one base to another, and then how to generate the complement of the binary number. And you've studied two systems. One was the diminished regex complement, and the other was the regex complement. And you perform the subtraction operation for the signed and unsigned data by using the regex complement method. And for example, for the binary data, you've computed one's complement and two's complement. Then you've discussed different binary cores and their implementation. So this was all which you've studied with Dr. Sadek. That was basically the chapter number 1 of the book Digital Design with Introduction to Verilog HDL. So as far as the reference seedings and acknowledgements are concerned, we are still at chapter number 1 of the Digital Design with Introduction to Verilog HDL by Maurice Mono, and I've got 5th edition. And these slides are basically the primary structure of the slides are designed by Khalid Ibrahim, Sir Khalid Ibrahim, and we are using the same template which he used to follow for his classes. And so let us start our discussion with the basic logic gates. So basic logic gates are also known to be the primary gates, that are the basic components in order to design the digital systems or circuits. So in today's session, we will be discussing the primary gates that are NOT gate, AND gate, and OR gates. Then we will switch to the NAND and NOR gates. Afterwards, we will discuss De Morgan's theorem if you got some time. Otherwise, we will continue this discussion in the next session. Then we will focus on exclusive OR, that is known to be the XOR gate. Then we will discuss the multiple input gates other than the standard two inputs gates for the normal gate operation, or one input for the NOT operation. We will see how multiple inputs are handled by these logical gates. And then we will discuss the logic gate ICs which you used for your lab experiments, that are the 74 series ICs. Mostly the ICs are 74 series which we are utilizing for your lab work in order to design the basic digital circuits. Okay, so to start with our discussion with the NOT operation or the inversion operation, basically NOT gate is a component that basically inverts the Boolean variable or the literal and produces its inverse result. For example, we can say that any Boolean variable or literal can have possibly two values. Right now it's at this stage. For example, we've got a variable x, and x is a Boolean variable or Boolean literal that can have a possible value of 0, and 0 is definitely associated with some sort of physical phenomena, and 0 do have some sort of proper representation that is dependent upon uh, the technology or the implementation in which that is been considered. For example, in the TTL standard, that is the transistor logic standard, the 74 series, the IC which you are using in your lab experiment, The definition of zero in terms of voltage is 0 till 2.2 volts, and for the logic one is 3.3 volts till 5 or 5.5 volts. So these zeros and ones definitely are associated with some sort of physical phenomena. And the other possible value, that is definitive value, that a Boolean variable can have a 1. So as far as the physical phenomena are concerned, as far as the Boolean logic is concerned, 0 can be associated with off state, 0 can be associated with false state, 0 can be associated with invalid state, and so on and so forth. As far as 1 can be associated with on state, 1 can be associated with true state, 1 can be associated with valid state. So if we are defining 0 and 1 in this context, then we are using the positive logical systems. And if we are inverting the definition, for example, 0 is associated with positive things and 1 is associated with negative things, then we are considering the negative logic system. So till now, at this point, we've got two definitive values. X is a Boolean variable that can have a possible value 0 or that can have a possible value 1. Later on in the later stage, we will discuss that the X can have also two possible values. One is the undefined state and other is the high impedance state. So that is been undefined state has been labeled as X. So let me change the variable so that you don't confuse this X with this X. So let us assume that we've got a Boolean variable that was A, so that you don't confuse that with that. This is the state, this is the value that any input or output pin in a digital circuit can have. And the fourth possible value can be the Z state, that is the impedance state. Normally the Z state is mostly utilized in tri-state gates, which we will discuss later on in our second session portion. So since we are starting with our basic definition, so right now I'm skipping the definition for the X and Z, these literals. So on later stages, I will definitely going to define these stages as well. So as far as the NOT operation is concerned, whatsoever you are in a state, for example, you are in a 0 state, the inversion of the 0 is 1. So you'll got 1 at the output. And similarly, if you apply 1 at the input, 0 will be produced at the output. So this is the symbolic representation for the NOT gate or logic symbol for the NOT gate, where X is the input, Y is the output, and we are performing the NOT operation. One thing, don't confuse this symbol with this symbol. This is a different thing. This is a different thing. This is a different thing. So you have to be very careful while defining the logical representation or symbolic representation for those digital components. This thing is not equal to this thing. This thing is not equal to this thing. So you have to be very careful. This thing is known to be the buffer, this thing is known to be the tri-state gate, and this is the symbolic representation for the PN junction diode. So this is not equal to NOT operation, this is also not equal to NOT operation, and this is also equals to NOT operation. You have to be very careful while using the symbolic representation of any discrete or digital component. What is this thing? Let me highlight that. This is basically the Boolean function that is describing the behavior of that digital component basically. So that is saying that Y is the output. So normally the Boolean functions can be represented in that particular format. We've got a function. So the function basically, for example, we've got a system here that have three inputs, A, B, and C. This is a digital system. For example, this is a system, and we've got an output that is known to be, for example, D. So basically D is a function of A, B and C. So we can say that output D basically that is dependent upon three literals that are the input literals. So D is a function of A, B and C, and how this output is related with these input. Basically Boolean function describes that. Boolean functions basically relates the outputs with the input and how those inputs are processed in order to generate that particular output. So we have got an output y that is a function of x and that is equals to not x. So not can be symbolically represented in equation by this symbol. We will learn that not can also be represented with, for example, a bar on a Boolean literal, or we can say that we've got x literal and x prime basically that represents the not operation. So these are the alternative representations of the not operation. So as far as the inversion is concerned, here in this representation we can see that the q is the output that is a function of the input a. So q is equal to a prime. Basically we are performing the not operation. So not can be described in different ways in different platforms. For example, if we are using Verilog or we are using MATLAB, Verilog is a hardware descriptive language in which we're going to describe our digital designs. So if you have to use the not operation by using gate level modeling, or you can compare that, since you have the programming experience, you are the computer science students, you just have can compare that thing with C++ here in order to understand that. So in Verilog we use the syntax in order to represent not operation. This is the syntax. Similarly in VHDL also a hardware descriptive language that stands for very high speed integrated circuit hardware descriptive language, and we have to represent the not operation by this expression, or we can use this expression to represent not operation. And in order to describe a not gate using Verilog, we will use this primitive, or this is the syntax for describing the not gate. Since you haven't studied Verilog, so I'm not using those terms. For example, the primitives and what are the primitives, what are the gate level primitives, and what are the modeling techniques which can be used in order to describe any digital component. So to conclude with, the NOT gate basically is a gate that inverts your inputs, the status of your inputs. If you applied 0, you'll got 1, and if you applied 1, you will got 0 at the output. Now, if we add the NOT gate in series, we use this term cascading the terms. So if we cascade the NOT gates, and if the number of NOT gates are even, for example, we are using two NOT gates in series, so basically they usually cancel out their effect. So if you use the NOT gates that are in odd basically, so here you can say that for example in this example we applied x has been inverted, then it's been double inverted to give x, so they basically are cancelling each other's effect. So this is just the same as a wire basically. So if I don't use NOT gate, it's sufficient. As far as the cost analysis is concerned, the first approach basically is a costly one, since I have to pay for the two NOT gates, while the second one is just a wire. I don't have to pay anything extra. But if these NOT gates are cascaded in such a way that the number of NOT gates are odd, for example, let me draw in front of this gate that we've got another NOT gate here. Now in this particular case, we are getting the x prime. X is been inverted here to x prime is inverted here to x, and then x is been inverted to x prime. So we can replicate all those NOT gates that are in odd number with a single NOT gate. X and x prime. So these configuration basically both are equivalent in terms of producing the result. Now, which one is economical in terms of resource utilization? You can clearly say that this inversion operation can be performed by using a single NOT gate, while in the above expression or above logical assessment or diagram, we are using three NOT gates, whereas the result of both the expressions are same. Now coming to the AND gate. AND gate basically performs the AND operation. You can assume that the term AND which we use in the linguistic is the same term to link up the two phrases or two terms. And here for the AND operation, we can say that if both the literals are true, then the output is true, or you can say that if both the literals are 1, then the output is 1. Basically, we can say that AND gate provides the logical multiplication. It's not the binary method, decimal multiplication or basic multiplication. It performs the binary or the logical multiplication, which you can say that if you've got the two inputs x and y, and we've got the output z, and we can see that when x and y are equals to 1, then the output is 1. In all the other cases, the output is 0. So it is basically multiplying the inputs, logically multiplying the inputs. So as far as the expression of the Boolean function is concerned, we can say that z is a function of x and y, and that is represented by this AND operation. And basically, in a Boolean algebra, we're going to study later on, we are using two operators. Basically, one is a dot operator, and one is this OR operator. This dot operator basically represents the AND operation, and this plus operator basically represents the OR operation in Boolean algebra. So I can also represent z as x dot y. So as far as the representation is concerned, in MATLAB we can represent as x and y. In VHDL we can represent x with the keyword and y. Uh, x direct y can also be represented as an AND operation. In your textbook, it's x dot y. Basically, that is the AND operation. And if we skip that dot, that is fine. Basically, we are basically using the AND operation between two literals. And in Verilog, we use the AND primitive and command, because you can say that it's a command or a primitive that is basically describing the AND gate, where z is the output and x and y are the inputs. So as far as the analogy of the AND operation with respect to switches are concerned, so we can assume that AND can be replaced by the two switches that are connected in series, and if both the switches are closed, then the circuit is complete and the current is flowing from the circuit. And if any of the switch is open, then the current is not flowing from the circuit. For example, these are the series switches, and here you can see that these two switches A and B, if A and B, any of the switches open, the C is 0 basically. And if we have to make C equals to 1, for example, this is the current that is been flowing in this circuit, then we have to close this switch also, and also we have to close the other switch also. By closed switch means logic 1, and by open switch means logic 0. Now coming to the binary addition, which we will be discussing later on in detail. This is the truth table. Truth table is a table basically that represents all the possible combinations of input and the response of the system on all those possible combinations. In this particular case, A and B are the inputs. These are the inputs. and S and C, basically these two are the outputs. And you can clearly see this carry output, that is basically the AND operation between the inputs. So later on we will discuss that how we're going to extract the terms in order to specify the Boolean function from the truth table, when we will be discussing the canonical and standard forms of expression of the Boolean function. So in order to implement the carry operation, we just have to use a single AND gate that is sufficient to produce the carry result for the 2-bit addition. Now coming to the OR operation, as far as the expression is concerned, if any of the input is high or all the inputs are high, the output should be high. Basically, you can assume a parallel operation between the switches as far as the previous example is concerned. So this is the logic symbol for the OR gate. Here X and Y are the input, Z is the output, and Z is a function of X or Y, and we can also say that Z is equal to X plus Y. X plus Y. Here this plus is not an addition operation. Basically, you have to be very careful. X is not added with Y. This is basically the OR operation here in Boolean algebra. So this is OR operation. This is not equal to arithmetic addition. Okay, so don't confuse both of the terms, and the context is important here. This plus sign is used in a context of OR operation rather than the arithmetic addition. So we can assume that the two switches are in parallel, and if the we have to get the current flown from this source till here, then if any of the switch is closed, the current can be flown. So open switches represents 0 and closed switches represents logic 1. This is the truth table here, and if you can see that if any or all of the inputs are 1, the output is 1. The output is 0 in only that case if A equals to 0 and B is also equals to 0. Here we can represent that in different ways. For example, in Verilog we can represent in this way, this representation, or this representation. In VHDL we represent in this representation, and in your textbook we are using different representations which we will use. Basically we will be using this representation in common. Let me highlight that. So properties of AND and OR gate, basically the commutation is properties also valid. For example, A or B equals B or A. That is same, just like the mathematical property of other integers or the decimal numbers. This is the property our OR operation. This is property our AND operation. So A and B equals B and A. So by changing the order of the inputs, the result is not affected by the order of the inputs, basically in AND operation and OR operation. So all of these things are basically same or equivalent or equal. Now coming to the associative property for the same operation, if A is OR with the B or C, for example, we have ORed B with C and then we OR the result of B or C with A, that is equivalent to A OR with B, then the result of A or B is being ORed with C. So in terms of logical gates, we can say that for the first expression, we've got B and C that are ORed. This is for example B, this is C, and the result of B or C is further ORed with A. For example, the result is X. So this is basically equivalent to or equal to. So I'm drawing in a bit hurry, so my drawing is not, you can say that the exact symbols, but you have to use the exact symbols. So if I ORed A with B and then OR the result with C, so these two things are equal. You can also prove that by providing A, B and C combinations, the value of A, B and C. This is for example Y. So here in this case X equals to Y. Similarly, same property is valid. Now coming to the distributive property basically. So the left hand side suggests that B is being AND with C and then the result is being ORed with A, that is basically equals to the A or B then ANDed with A or C. Things are basically equal. Now coming to the NAND gate. NAND gate is basically the inverse of AND gate. So we basically invert the output of AND gate by using the NOT operation. So basically this thing is equivalent to an AND gate, and output of AND gate is being inverted. This is X, this is Y. Here in this point we are getting X dot Y, X and Y, and here we are getting X and Y prime. So this thing is basically equivalent to this thing. So what we are doing, we are inverting the output of AND gate to produce the output of NAND gate. Here you can see from this truth table. Now these are the Boolean functions of the expression that are representing the NAND operation basically. So in our expression further discussion we will use this representation. For example, W equals X dot Y prime. And in this particular case basically this is Z. If you see this diagram, basically Z is the output that is equivalent to X dot Y full prime. That basically represents the NAND operation. So NAND is basically not AND, and which we have discussed that in detail. Coming to the NOR gate, that is basically the inverse of OR operation. So we are using a NOT gate in order to invert the output of OR gate. So that represents the NOR gate here. We can see that from here, from this representation, the output of OR gate is inverted to produce the output for the NOR gate. So as far as the symbolic representation is concerned, we can use this as this OR gate that has been inverted. For example, A and B are the inputs and Y is the output. So here we are getting A plus B or A or B, basically A or B, that is been inverted to produce Y. So Y is equal to A or B full prime. And this is the truth table that represents the NOR operation here. This bubble basically or circle basically represents the inversion operation. So in any digital circuit, if you see any circle in front of the symbolic representation of any digital component, that basically represents the NOT operation and the hollow bubble. And if that bubble is filled, for example, we have got cross wires here and we are using this fill. This is not the inversion. Basically this represents the junction or the connection between the two wires here. So there is a difference between this circular representation with discrete components or digital components and this junction or node to interconnect two elements here. So this is the representation here. W is equal to X or Y and Z is basically equals the inversion of the OR operation, which you can see from this truth table. You can see from these two lines here. Well, student, that was all for the today's session. That was the basic introduction with these gates, and I hope so you are very much familiar with this setup. And as you are using the labs and implementing those components in your lab in order to implement some digital systems. In our next session, we will be focusing on the De Morgan's theorem basically, and then we will discuss the canonical and standard forms of expression, and then we will discuss the Boolean functions in detail. Till now, have a good day, and inshallah, we will meet next week.